That's not a good condition. Cool. Actually, it's already 2:35. So I think we're just going to start. Hey, guys. No worries. Cool. So let's get started. Today, we're going to continue to talk about scene representations. Let's start with a refresher of what we discussed last time. So there's going to be some refresher, and there's going to be some part that we didn't get to. Actually, show of hands, I'm curious. I think I slowed down over the last semester. So who thinks I'm going too fast? Okay. And who thinks I'm going too slow? I'm going exactly right. Okay, good. That's a big improvement. Cool. Okay, so like some still on the fast side, but not fast. Okay, good. I'm just making sure. Please say if like I'm belaboring a point, it's okay to like come to me afterwards and let me know. I'm still figuring out the right pacing for this lecture. Okay, cool. So today we're going to talk about 3D representation some more, and then if we get to it, we're also going to start talking about rendering in conventional computer graphics. Or it's basically in this course we're going to have like a one lecture, very compressed summary of like conventional physics-based rendering, just so that everyone gets an idea of like how conventional physics-based rendering looks like. It's getting more important for differentiable rendering and for 3D reconstruction as well, but it's not currently the most important topic, but it's still really important to kind of know on a high level how it works. But before that, we're going to do a brief refresher on 3D representations and talk about something that we didn't get to last lecture. So let's just go through what we discussed in the last lecture, in the last two lectures, actually. First, we talked about depth maps, right, and a little bit about normal maps. And we actually already had one lecture about how can you actually train neural networks to predict depth maps and to predict normal maps. And that was really cool. Then we talked a little bit about actual 3D representations. So we called these 2.5D representations because basically for every pixel, they kind of give you the third dimension, but they never tell you about like what's behind. So they don't actually parameterize the whole scene. They only parameterize the geometry of visible surfaces. Then we talked about our first instance of actual 3D representations, which we kind of called surface representations. These are, for instance, point clouds or meshes. And these basically give you the geometry of all of the 2D surfaces that are embedded in 3D space, but they don't tell you anything about any other position in space. And in practice, that has a few implications. One of the implications is that there are some queries that are kind of hard to answer with these representations. We said, for instance, if I give you a point in 3D space, it's hard for you to tell me, does it lie inside or outside of an object, if you just have the point cloud, or if you just have the mesh. But we also discussed that these kind of surface representations are actually what is being used in computer graphics a lot today. And these are extremely relevant, even though in 3D reconstruction, interestingly, they're not currently used much. And then we briefly talked about field representations or field representations. And what did we call a field parameterization? We basically said, oh, there's this definition of physics of fields. Field basically just means it's a function that is defined over coordinates. So for instance, you've all heard like the space-time field or something like that, right? That's just meaning like, oh, it's a function that maps every coordinate in space and in time to like something. And so this is something, this is naming that we have imported. And so maybe, for instance, you've heard of the radiance field or the signed distance field. These are called fields because they are defined over coordinates. And we, for instance, talked about the sign distance field, which is one way of parameterizing the geometry of things that are in 3D space. For instance, let's take this chair here. If you took the sign distance function of this chair, the sign distance function for every point in space tells you how far it is away from the closest surface in space. So for instance, here the point would maybe be 50 centimeters away from the surface, and hence this point would be mapped to 50 centimeters by the sign distance function. Therefore, all of the points that lie on the surface would be mapped to 0 by the sign distance function, and that's then how surfaces are defined. For sign distance functions, they are defined as the 0 level set of this function. And if I give you this parameterization of 3D geometry, it's much easier to answer certain queries. For instance, it's very easy to answer if a point is inside or outside an object, because inside the sign distance is always defined as negative, outside it's always defined as positive. But again, then it gets harder to answer other questions. So for instance, if you want to have the set of all points that lie on the surface, that gets really hard, because I just give you this function, and now you first have to find the points that lie on the surface. So you first have to find the 0 level set. And that is actually something that is not straightforward, and it's kind of expensive. We discussed one algorithm to do that, which was this Marching Cubes algorithm. Okay, this is just a high-level summary. Okay, so now what we didn't talk about for these field parameterizations is how do you actually parameterize functions in 3D. So let's say, for instance, we have a 3D function, and I promise you soon we'll get to like cool, pretty images. But for now, let's just imagine we have like these abstract 3D functions in space. For instance, let's say we had a sign distance function. You had this room here, and you wanted to parameterize the room, the geometry of this room, and you wanted to parameterize it as a sign distance function. How would you actually parameterize that sign distance function? By which I mean is if you are sitting in front of your notebook and you want to have a Colab and you want to import this room, what would be the format of this room if it was a sign distance function? And the first thing we talked about was kind of voxel grids, right? The voxel grid is the thing that almost all of us have dealt with. In 2D, everyone in this room has dealt with them, which is just pixels. Images are usually stored as voxel grids, which is just grids of pixels, right? In 3D, of course, there's a straightforward equivalent, which is just you have 3D grids. And for instance, in the sign distance function case, the sign distance function, like the voxel, every voxel might just store the sign distance value. Done, easy. And then you can kind of interpolate within voxels to get like continuous sign distance functions with linear interpolation or cubic or whatever you want to do. Okay, good. We already talked about a few practical problems of these voxel grids, which is that for 3D, like 2D images, like large images already get pretty, I mean, actually even today, if you're sitting here with your laptop, if you have like really high resolution images and you like are sending them over to someone via Slack, it already gets painful. There might be like 100 megabytes. Sometimes, if your internet is slow, it takes a few minutes. Okay, so now imagine you have like a voxel grid sign distance function, and you have like a really high side length. These things get huge. Like they can easily be on the order of like billions or trillions of values. So it kind of get expensive because the memory that you acquire grows cubically with the resolution that you have. So long story short, these are actually just literally intractable in higher dimensions. So if you have like a space-time voxel grid, like 4 dimension, that gets like really expensive. Okay, so the first thing that is worth talking about here is a classic computer graphics trick, which is called like multi-resolution representations. And one classic multi-resolution representation is the octree. Who knows about octrees? Some people, great. So the idea of an octree is actually pretty simple. Like there's a bunch of algorithms that you would then have to learn how to actually work with them algorithmically. But the basic idea is simple. What you want is you want to have a spatially adaptive resolution for, like you want to basically have side lengths of each voxel that is spatially adaptive. So in different regions in space, you want to have different side lengths for like a different resolution. And that makes sense if you look at the room here, right? The room here is mostly air. So how many voxels do you need to parameterize air? As few as possible, right? Like ideally you would cut this room in half and say, or like, I don't know, you would cut this room into like quarters, and then there's a whole quarter you would just want to have like zero, you didn't want to store any values in there. You would want to use as little memory as possible to store values in there. And so that's exactly what octrees do. Octrees basically say, take the voxel grid and now split it into 8 smaller cubes. And in each cube, basically check if there is something in the cube. If there's nothing in the cube, then just like leave it as is. You just needed one value to store that there's nothing there. But now if there is something in the cube, maybe consider subdividing it into 8 smaller cubes, and then subdivide it again into 8 smaller cubes recursively until some stopping criterion. And so what you can get is if you have these rather complicated surfaces, like let's say, for instance, here the surface has significant curvature, right? There's lots of air. For the air, you want to have as little memory as possible. And then there's like some curvature. And wherever there's like finer detail, you want to have more voxels. Yes?
Does it operate on meshes or signed distance fields or what?
Great question. So it operates, it's a discretization of 3D functions. It's functions that are defined in 3D. Any 3D function you can, so really the way, the abstraction that I think about always is you have a function that is defined, that takes a 3D coordinate as input and tells you something about that 3D coordinate. And now you want to find a way of storing that function on your laptop. Like, how do you discretize it? That's basically it. And so the signed distance function is a good example for.
Does it have to be, like, would a mesh work, for example?
A mesh? What do you mean a mesh would work?
When you say like a function, I'm thinking like a continuous function.
Yeah.
Like any coordinate. But like a mesh is sort of like, there's some notion of discretization.
So a mesh is just usually a mesh is not, so mesh is actually an overloaded term. In this lecture, we've only used it to refer to surface meshes, which are basically 2D surfaces embedded in 3D. So the meshes we talked about in this lecture don't actually parameterize 3D functions. You can convert a mesh into a signed distance function, right? You can take the surface that is parameterized by a mesh and then say, I'm interested in getting the signed distance function that is converting this into a signed distance function. But the mesh itself isn't a 3D function. But with respect to overloading, technically this is also a mesh. Like some people in like finite elements, like there's many fields where people talk about 3D meshes, which are basically just graphs in 3D. But we don't refer to it, like that's not the meshes we're referring to. We're just referring to the surface meshes. Okay, yeah, and so basically the basic idea is how do you build an octree? You take the initial voxel grid, you divide it into 8 voxels. If any box has more than, like, so this is for instance to like deal with, like let's say I give you a point cloud and you want to turn your point cloud into like an occupancy voxel grid. So like you want to end up with a voxel grid where every voxel tells you whether there is a point in it or not, right? Then what you would get is basically like this like thin shell of voxels. So one way how you might do it is you take your point cloud, you put it in a voxel grid, you split it into 8 voxels, and then for each voxel you ask how many points are in this voxel. And if there's smaller than n, then you stop. If there's more than n, you subdivide it, and you do that recursively until in every voxel there's only 1, for instance, and then you will end up with this like octree. There, I put my phone. There. Okay, makes sense. So this is just something to heard of. We'll actually. Yeah, and this is now interesting. This is a trade-off that you'll always be facing. So this, what does this do, right? It's interesting. It saves memory. So when you store this voxel grid, it saves you a lot of memory because you're wasting less memory on like things that are empty. But it actually increases the time that you take for querying the function, because now if you query the function, you can't just go into the right index and retrieve the value there. Now you have to traverse a tree, which is like this tree of subdivisions, to like figure out where in your array you actually want to query and like the arrays that store these voxel grids are like these octrees are also a little bit complicated. But this is not an algorithms lecture. If you go into an algorithms lecture, you might have actually built an octree and like dealt with this kind of index shenanigans. But this is just something to be aware of. Once you build an octree, then like you need special algorithms to query it quickly, and then there's all of the stuff with like n log n time to like get a value and whatnot. But it's still, I should say, it's still pretty fast. So like even if you have like in 3D computer graphics, when you build an octree like that and you want to get a value, it's still a really fast data structure to query. It's like, okay, now we're going to talk about something which I had mentioned already was the topic of my PhD and the topic of much rage over the last few years. So we're talking about neural fields. So neural fields are a magical topic in the sense that the first time you hear it, just like me, probably back then, it sounds like sounds so cool. It sounds like such a cool idea. And it is. Okay, so what's the idea of neural fields? The idea is to say the following. Okay, so we have this function. This function is defined in 3D, right? And this function, for instance, it might parameterize the signed distance function of this room here. And this function could be really complicated. It could be like really, really complicated in the sense that it might have like lots of high frequency detail. It's like a really complicated function. How can we parameterize this function efficiently? Voxel grids are huge, so it's like really expensive to store voxel grids, so that's not good. But we have these universal function approximators recently, since 2012. So can we parameterize our function as a neural network? So you literally go and you say, okay, the sign distance function, we're going to parameterize it as a neural network. So it's going to be a neural network, and it takes a 3D coordinate as input, and as output, it's going to give you a single scalar, which is the sign distance of that point, for instance. Or take the occupancy function as another example. We talked about occupancy. It's like empty parts of space and then occupied parts of space. The occupancy function tells you empty, 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 occupied. Same story. Has lots of high frequency details. Storing it in a voxel grid is really expensive. Why not store it as a neural network? And this is exactly what people were thinking about in 2018 and 2019. This is also what I was thinking about in 2018. So these are the seminal papers from that time. Occupancy networks, learning 3D reconstruction in function space. IMNet, learning implicit fields for generative shape modeling. DeepSDF, learning continuous sign distance functions for shape representation. And then mine was actually, I should say my paper was inspired by these, but my paper also uses, this was the paper that started for me, like much of my research stuff. Okay, but this is basically the idea. The idea is really just, okay, we have the space, we have this like, in this case, it's a 2D function, right? Like an image, this is an image, right? And how do you parameterize an image? You can parameterize it as a grid of pixels, and then you store the pixel values in an array, or you can parameterize it as a neural network. So you just have a neural network, it takes a 2D pixel coordinate as input, and it gives you the color at that pixel coordinate. And why is it intuitively, why does this sound like such a cool idea? So yeah, actually, let's well, first I'm going to show you what it looks like. So let's say, for instance, we have this, we have the shape. The shape is parameterized as a point cloud. Now let's say we could like get the occupancy of the shape. So this is a little bunny. Imagine I gave you the ground truth, like the ground truth occupancy function of this bunny. So you could query any coordinate, and then you would get the occupancy for that coordinate. Of course, you can go ahead and you can just train like your neural network on top of it. And then this surface here, what you're seeing here, is actually obtained with this Martin cubes algorithm that we were discussing. So once you can just take your neural network, you train it on the ground truth occupancy. So what does that mean? You sample a 3D coordinate and you get its occupancy, and then you give it to your neural network and you train it to just reproduce the occupancy function, right? So you can do that, and then at the end you can extract the surface via like Martin cubes, and you can visualize it. Why is this intuitively so cool? The reason why it's intuitively so cool is that neural fields apparently, and this is true, they really do that, are kind of like a multi-resolution, very compact multi-resolution representation that is also continuous though. So what it fascinated so many people about neural fields back in the day was that, and still today, is that the neural network is a perfectly continuous function. So it maps every 3D coordinate to a value at that 3D coordinate. Right? It's not just you have like values stored at like certain locations and then it's okay. And intuitively, what the neural network does is during training time, the neural network will allocate the parameters of the neural network to kind of, in some sense, I wouldn't say optimally, but in some sense, optimally represent the detail on the surface of the shape. And what ends up happening is that once you fit a neural network to your shape, the weights of the neural network might be really small. It might be like a few hundred parameters that can encode the shape, and the way it's encoded is just in the parameters of the neural network, right? Please feel free to interrupt if you have any questions. So, okay, so this seemed like a great idea, and it worked really well. So like these first few papers that I just showed you, they did this really cool thing where they encoded these like, funny little shapes, and they had like lots of, they had like some generalization in there and whatnot. It was cool. But then when people were trying it on larger scenes, like for instance this room scale scene, if you just take a ReLU neural network, which is what back then everyone used, if you use the ReLU neural network to like parameterize this like large 3D scene, it would look something like that. So somehow the ReLU neural network didn't quite get it. And so this was something that isn't only true for 3D scenes like this one, it's also actually true for images. So like seemingly you could take this image and the same should hold, right? You should be able to like just train a neural network to reproduce this image like that. And in fact, you can, but what you'd find is that the neural network will kind of smooth over all of the fine detail in the image. The ReLU neural network will not be able to capture the high frequency detail. And you might be compelled to do the same thing with audio. So maybe you can fit your neural network to audio, and it seemed like a really cool idea. Well, then we have the parameters of the neural network to like encode the audio signal. And there could be many reasons why you might be excited about it. Back then, I thought, well, this will give us like a cool representation for doing machine learning on top of these signals, because now the signal is encoded as a part of the neural network, and it's going to be all cool. And well, audio also didn't work really well. And so then a number of people came up with ideas of solving this problem. And one of these papers was a paper of mine, which is called Siren, Neural Implicit Representations with Periodic Activation Functions. I should say why neural implicit representations was basically what we called it before we called it neural fields. So I introduced this to you as a neural field. Like it's we discussed this formulation of a field, which is a function that is defined over coordinates. People then said, okay, if we parameterize this function as a neural network, we're going to call it a neural field, because it's like a field parameterized via a neural network. But in the very beginning, people called them neural implicit representations, and the reason for that is that when you look at sign distance functions and occupancy fields, we say that these are implicit representations of the geometry, because the geometry, you don't have parameters that define the geometry of the shape immediately. You always have to first find the zero level set to get the geometry. So these were called implicit representations of geometry. So we called these neural networks that parameterize these sign distance functions neural implicit representations. So what was the idea of Siren? What we did in Siren was intuitively very simple. We said, okay, so here's the ReLU neural network. For a few reasons, it should work better, and we're going to talk about in a moment why. It should work better to, instead of having a ReLU activation function in the neural network, replace the activation function with the sign activation function. So now, instead of having a neural network with ReLU activations, we're going to have a neural network with sign activation functions. And what was quite impressive at the time was that when you use that neural network to fit these signals, you were able to reproduce each of these signals basically perfectly. So for instance, the image, you could reproduce the image perfectly. So this is stored in the weights of a neural network. This room scale scene, you could also directly import in the weights of a neural network, an audio signal, or even kind of differential solutions to differential equations, which we're not going to talk about too much. And intuitively, this is this is how we came up with it back then. And this is something that is cool to understand about ReLU neural networks in general. How do you think about what a ReLU neural network actually does? You definitely have probably learned about like hyperplanes and ReLU neural networks before. Does that connection seem something? Imagine you have your three-dimensional input, which is your three-dimensional coordinate that goes into your neural network, your neural field at the input, right? So your neural network takes this 3D coordinate and outputs like a sign distance value, for instance. Now, if you have a ReLU neural network, what is the first layer of your ReLU neural network actually doing? So let's think about that for a brief moment. So what is the first layer of your ReLU neural network doing? Like it has the ReLU activation function. This is written as a function, so it takes like some input, and it's like ax plus b, right? Ax, x being the input coordinate, a being some weight matrix, and b being the biases of the network, right? And then you have the ReLU activation function on top of it. So what is this? If this is a 3D coordinate, each row of this matrix actually defines one plane, right? Because like it's a dot product which basically defines the direction, and the bias tells you how far away it is from the origin. So basically, each row of ax plus b gives you one plane in the input coordinate space. And then the ReLU activation function basically says how far away, like for all the points that lie on one side of the plane, I'm going to just give you the distance from the plane. That's going to be the output of the neuron. And for all the coordinates that lie on the other side of the plane, I'm just going to give you 0. So let me draw that just for a moment. So basically, in 2D, you can imagine it like this. This is like your input space. If you have ax plus b, if you have like one vector ax plus b, then you'll have it that defines like a thing like this. This is in fact going to be a vector a, and then this is like kind of simplified, and then the b is basically the distance, the offset from the origin. And then what does the ReLU do? The ReLU says everything that is on this side of the plane gets a positive output, and everything on the other side is set to 0. So that's what the ReLU neural network does. So actually, if you go back to this little bunny and you look very closely, I'm not sure if you can see it. Here on this little bunny, you can kind of see that there's kind of little edges on the surface if you look closely on the shading. And it turns out that if you parameterize a shape with this neural implicit representation, and you zoom in really closely, you can actually see like lots of tiny facets. And that's because what the ReLU neural network does is at each layer, it basically does this. The first layer you can imagine just as these hyperplanes, but it turns out that even the higher layers of the ReLU neural network, you can always like visualize them in the original input space, which is in 3D. And basically, you just divide the space into thousands of tiny, tiny little buckets, like little hyperplanes. And you can actually, turns out you can actually see these hyperplanes here. And now what you have to imagine, of course, is that now when you want to fit the shape, what has to happen is that all of these hyperplanes have to move, and all of these hyperplanes have to anneal onto the surface of your object. So if you have an object with like lots of high frequency detail, like all of these little hyperplanes kind of have to wrap around your object, and it's kind of a piecewise linear approximation of your object. Like ReLU neural networks are literally piecewise linear. Like the output of a ReLU neural network, if you zoom in really small, you'll just see lots of tiny piecewise linear pieces. So this is kind of, in fact, a piecewise linear approximation of your shape. But the intuition that we had back then, was basically like, look, like your ReLU, each ReLU unit in your neural network really just has one kink. So it just has like one in the input space, right? Your ReLU neural network your ReLU unit really does only one interesting thing, which is at the kink. So this function here is linear on this side, and on this side it's just 0. And this decision boundary is only really one decision boundary. So there's not that much interesting stuff you can do. Versus the sign activation function, right? If you think about what the sign activation function does, it will actually look like this as well, but instead it'll give you a sign. So it'll give you like lots of activations throughout the input space, as opposed to just like one little kink to do something with. So that was like one piece of intuition. And then maybe the more important, interesting piece of intuition is the following, that the ReLU activation function for being piecewise linear, what does it mean to be piecewise linear? It means that if you take the first derivative of a piecewise linear function, it's piecewise constant. If you take the second derivative of a piecewise linear function, it's 0 everywhere. So in fact, the second derivative of a ReLU neural network is 0 everywhere. So if you do like just autograd, and you take two gradients of your ReLU neural network, it's just 0, always. And so there's an interesting little thing, which is that there are some functions where there are some functions that you are interested in fitting that have interesting higher order derivatives. In other words, right, you all know about this function approximation theorem for neural networks, right? Everyone is like, this is something we all get told. This is why neural networks are cool. You can approximate any function with a neural network, right? And this statement is kind of overused because actually it's complete garbage. And it's complete garbage in a very specific sense that this statement is true only in a very specific sense, which means that you can arbitrarily closely approximate any function. Like you can get arbitrarily close to like approximating a real function, like any function in with a ReLU neural network. But in practice, let's say, for instance, your function has a higher order derivative that is interesting. If you have studied electrical engineering, you might know a few of these, like a wave function, for instance, has constraints on its second derivative, right? Well, a ReLU neural network doesn't have a second derivative. So by definition, your ReLU neural network will never be able to actually accurately parameterize the function you're looking for. If the function you're interested in has non-trivial second order derivatives, your ReLU neural network will not be able to do any reasonable job at capturing the true nature of the function. Other than in the original domain, it can get arbitrarily close. But like if you care about the gradient information, it's not there. It's just can't be there. Well, the sign has an interesting property, and the sign has an interesting property that every derivative of the sign is a sign function itself. So no matter which order of gradient you take, the sign always stays smooth and continuous. So that was the intuition we had back then. And this was kind of the video that we made for the paper. So this was, on the left-hand side, you can see a sign distance function parameterized by a ReLU neural network. And on the right-hand side, you can see a sign distance function that is parameterized by this sinusoidal representation. But we called it sinusoidal representation networks because the siren it had a cool short. But this is really noteworthy. This whole room is stored in one neural network, which literally you give it a 3D coordinate, it tells you the side distance function for the 3D coordinate. And so this whole room, I think, is stored in like a 2 megabyte neural network. So it's like really small. Oh, never mind, 1 megabyte. So the mesh that generated this thing was, in comparison, 110 megabytes. Okay, so I told you my intuition for why it worked back then, but maybe, honestly, like looking back, maybe I shouldn't have. Maybe I'm going to take it out next year. Because actually, by now, we have a much better idea for why this works that is slightly different from my intuition back then. So So many people got very excited about this back in the day, just like me, because they somehow thought this has something to do with machine learning. Or like this has something to do with neural networks and with like generalization, or with like it has any relationship to artificial intelligence or learning whatsoever. When in reality, and you might be able to guess this already, when in reality all of this has actually nothing to do with machine learning whatsoever. And you can kind of tell by the fact that like your neural network isn't really learning anything, right? You basically imagine you fit a neural network to an image. What is the neural network going to learn about the image? It's going to learn nothing about the image. It's kind of like you have a grid, and like if you have a pixel grid, what does the pixel grid know about the image? The pixel grid knows nothing about the image, right? Like it's in a sense that the pixel values that you store are uncorrelated with any semantic information that you might actually want to easily access. You always have to process them to get something interesting out of them. Like you have to stick them into a convolutional neural network or something. And the same fundamental thing is true for neural fields. So for instance, you might learn like, you might know neural radiance fields, which we're going to talk about later in this talk. Neural radiance fields, many people got, it's even in the name, right? It's like neural radiance fields, kind of suggesting that this has anything to do with machine learning or artificial intelligence, because that's, back in the day, we thought that might be the case. In reality, it has nothing to do with machine learning whatsoever. It has nothing to do with AI. It is just another way of representing a 3D function, just like a voxel grid. So your neural radiance field or your neural field is exactly as smart as a voxel grid that parameterizes the same signal. And so what then is interesting about neural fields in the first place, or what is interesting about them at all? And there is something special here, which we're going to talk about, and I'm going to try to do a good job at explaining it. Last time, we actually talked about interpolation. We talked about bilinear interpolation. Who remembers our brief stint into bilinear interpolation? Okay, good. So we talked about, you have a function, and what did bilinear interpolation mean? It meant that you had a grid, and the grid stored values at every like vertex, right? And now you wanted to query a coordinate that didn't fall onto one of the grid values, and what did you do? You interpolated the 4 values on the corners to get the value of that grid. Okay, it turns out that what your neural network is doing, that you're fitting to this 3D function, can very well be understood in such a so-called kernel regression framework. And what does that mean specifically? It means that for your training set, let me give you an example. Let's say I gave you some weird shape. Okay, this is a weird shape, right? This is in fact a function defined over R2, because you can parameterize this via its occupancy function, right? You can parameterize this via a function that maps every 2D coordinate to either 0 or 1. And it's 1 if it's occupied, and it's 0 if it's not occupied. So the occupancy function will be 0 outside, and will be 1 inside. Make sense? Okay, so now imagine that your training set for your neural network that you're fitting to the shape would maybe look like this. So you would have like lots of points on the surface maybe. You would have some points outside the surface, and you would have some points inside the surface. Make sense? So you just sample this function, and you train your neural network on the samples of the function. Does that make sense? Good. Okay, so now what is your neural network doing? Your ReLU neural network or any other network that you're fitting on this thing. It turns out that the output of your neural network can always be expressed as a function after training, I should say. After you train your neural network, the output of your neural network can always be expressed as a function of the training points. The way it can be expressed as a function of the training points is very specifically by a kernel regression. And kernel regression basically means that you can always predict, like after training a neural network on like some training set, you can always predict the output of the neural network after training on any 3D coordinate or like on any new coordinate that you feed to the neural network as an interpolation of the training values. And this was a paper called the neural tangent kernel. Who has heard about the neural tangent kernel before? So people that do like lots of like machine learning theory, this was kind of a big deal like some 3 years ago. By now we've kind of, I think, moved on a little bit. There's like new theories which I'm not as deeply familiar with. But this was actually like a huge deal. This is like a huge deal when people understood it. And the specific way in which this works is kind of like this. The xi here and the xi here are, imagine each of these training points is an xi. So this might be x0, x1. So each of these training points is an xi. And then the y is the label of that point. So for instance, the label outside might be 0, right? The label inside would be 1. And the output of the neural network after training can be written like this. This is an idealized formulation, but we're going to say in a moment how it's idealized. The output of the neural network after training can be related to this equation, which basically says you have some kind of kernel function, which basically tells you the distance of your input coordinate, where you're querying your neural network right now, relative to all of the training points that you trained it on. So you get so you iterate through all your training points. For each training point, you evaluate this kind of kernel function, which basically tells you how similar is the coordinate that you're querying to this training point. And then you're basically taking this kernel into a kernel matrix. It doesn't really matter. Basically, you end up interpolating you're interpolating the labels of these training points according to that kernel function as well. And now you might ask, what is this kernel function? It turns out that the kernel function is actually this, which is kind of really interesting. F here is the neural network. So the similarity between 2 points, x and x1 and x2, that are where x2 might be the point that the neural network was trained on, and x1 is now the point that you're querying the neural network with, can be expressed as the derivative of, like the gradient of the derivative of the neural network with respect to its parameters. So let's say the neural network would have 1 million parameters. Then this would be the gradient of the neural network with respect to these parameters. So it would be like a 1 million dimensional vector, for instance, if your neural network has 1 million parameters. At the input coordinate x1, dot product with the same vector evaluated at input coordinate x2. So like what does that mean very specifically? You take your neural network, you give it coordinate x1, you get an output, you take the derivative of the output with respect to every parameter of the neural network, that gives you one vector. You take your other coordinate, you give it to the neural network, you get an output, you take the derivative of that output with respect to every parameter again, and the dot product of that tells you the similarity of these two coordinates under this neural network kernel. So let me say intuitively what this means. Intuitively this means that if I'm querying my neural network here, the output of my neural network after training will be a weighted sum of all of the labels of my training set, weighted according to this kernel function, where the kernel function is I take this one, put it through my neural network, take the derivative with respect to the parameters, and take the dot product with respect to the same thing that I do for this. And this is going to be the output of the neural network. Does this kind of make sense? Yes? Yes?
Why is it only pairwise and not handwise?
I don't know. Good question. Why is it only pairwise? Sorry, how would it be? So it's like, it's a weighted sum in the end. So like it's a weighted sum of all of the things in your training. So you do it for every pair. Like you get one coordinate and you want to get the output of the neural network at that new coordinate. And you're going to compare that new coordinate to all the coordinates in your training set. Every single one. Okay. So the reason why I'm explaining this is not generally practical. You can actually do this for toy experiments, and you can like kind of show that this is true. This is also, I should say, an idealization. This is true in the ideal case of an infinitely wide neural network, which of course you generally don't have infinitely wide neural networks. But in practice, it turns out that it is kind of like sometimes not that far off. And the reason why it's important to understand this is because it's important to understand that there's no magic, there's no deep learning magic here. What your neural network is in this context is it's a souped up interpolation kernel. Is basically the lesson of the day. Like what is NERF? Like the role of the neural network in this like little thing is the role of an interpolation kernel. It's kind of like doing bilinear interpolation plus plus, kind of, except that the interpolation kernel is hella complicated, and it's like hard to write down in closed form. But there's no magic here. The neural network isn't really seemingly learning anything about the scene that you're fitting it to, if that makes any sense. It is an interesting question. The kernel is actually fixed, and now we're going to get to that. The kernel is a function of the architecture of your neural network. So, and this is now, we just talked about Siren, and we talked about the ReLU neural network. This is now why, turns out, the ReLU neural network was really bad at fitting high-frequency detail, but the same architecture with sign activations has a very easy time at fitting high-frequency detail. And now we can ask ourselves, what does this tell you about the kernel, about the interpolation kernel of the ReLU neural network versus the interpolation kernel of the sign neural network? Actually, maybe someone has an idea. Someone, ideally, who doesn't know the answer already. Like, ideas. Like, why could it be that one neural network might be really good at having high-frequency detail while the other one might not be? Like, what does it tell you about the kernel? Yes? It's an yeah, good. Great, excellent. So overfitting was actually one reason why people were really excited about this, like, neural tangent kernel thing. Like, in this context, actually, what does overfitting mean? Like, in the context of this neural, in the context of, like, neural tangent kernel, what does overfitting mean? Right, exactly. What it basically means is that the kernel is really peaky. It means that every training sample, what the neural network will do is for a 3D for an input coordinate that is close to a sample in the training set, like, it has to be really close to the sample in the training set to get the correct value. But the moment it's a little bit too far away, the value is basically garbage. So it basically means that this kernel, like overfitting, basically means that the kernel is really peaky. The neural network is really good at assigning the correct value to the values in the training set. It tells you something about the values that are not in the training set. So what might it tell you about the values that are not in the training set? So let me go back to this is actually great. I love this because you're just following the reasoning of like one paper. That is the second paper we're going to discuss. So like you're just talking through it right now, which is great. What did I want to show you? Yes, 1 second, sorry. Here, great. So this looks great. Oh my God. Okay, stay. Excellent. So what would you predict if you zoomed in really hard on like a 4x4 grid here in this image? You zoomed in really hard, and now you sampled the neural network at a value that is in between 2 pixels. What would you think the value would be? Yeah. Like look at this image. What does this image look like? It looks really blurry, right? So what does it mean? Like if the image is really blurry, what it basically means is if you zoom in really hard, you would basically expect that the value of the pixel in between 2 pixels is basically going to be the same as the value of the 2 pixels that are around it, right? Because it's like really blurry. The neural network failed to like fitting this high frequency detail, and the neural network is just like really blurry. So in fact, that's exactly what would happen. If you would zoom in here, the neural network in between is basically, what does it mean for this to be blurry? It basically means that the values of neighboring pixels, the values of neighboring coordinates are really strongly coupled, like, right? Does that make intuitive sense? Okay, good. And now, in this one down here, this one might be hard. Like if you went in and you like went in between 2 pixels, which might have completely different colors in this image, right? There's 2 pixels down here, for instance, that have 2 different colors, or like 2 different grayscale values. If you zoomed in and you sampled the neural network at a value in between those 2, what would you predict the output would be? It could be anything. You don't know. It could be anything because the neural network has clearly like it did a good enough job at fitting the neural network has basically overfit. It's like this is the idea of overfitting basically. It means that in between these 2 training values, you have no idea what the value will be. And this is exactly really what happens. If you zoom in on this image in Siren and you sample in between 2 pixels, you'll get like lots of high frequency noise. Versus if you take the ReLU neural network, the ReLU neural network will be really smooth. And actually, if you look closely, you can even see, this is a fun fact, here you can see this in these, when you look at the fitting of these ReLU neural networks, you can sometimes see these lines. And these are exactly this is literally one of the hyperplanes in the ReLU neural network. Like one of these planes in the ReLU neural network will be one of these lines. Yes.
Yeah, so with like neural networks, when you look at like the activations, they usually like they're sort of like this the activations are like in a high dimensional space. They're not interesting that like the hyperplanes in this case have some physical.
Yeah. Great question. Yes and no. So for a value neural network, they have a physical interpretation literally in the sense that you can, so to speak, pull them back into 3D and you can visualize all of these little hyperplanes in 3D. Like you actually know this if you took like a machine learning class, you can visualize the decision boundary of a value neural network. You can like visualize these decision boundaries. And there are closed form solutions, like there are solutions for this. Sorry, they're not closed form. There's iterative algorithms that allow you to find all of the intersections of all of these tiny little hyperplanes. But the problem is that these hyperplanes are not, their number is exponential in the depth of the value neural network. So like the deeper it gets, because basically this is very hand-wavy, but you can imagine the first layer gives you these very interpretable, nice hyperplanes. But then the next layer, right, takes the output of many of those takes the distance to many of these hyperplanes as input and then builds a decision boundary around that. And that hyperplane is not as interpretable anymore. But you can think about them as like planes like living in 3D, and that is a totally valid thing to do. If not, I don't know that it's very productive, but like it's something you can. Any other questions? Cool. Fun fact. To the best of my knowledge, please correct me if I'm wrong, the same we do not know for transformers. So if you train a transformer on a training set, we don't know what this kernel would be. Yes? Great. See, I should get updated on that. So maybe there's an update. From when is that paper?
Well, I did a series of papers.
Oh, I see. Okay. I have no excuse then. But like, stages of making the slide, I didn't know about that. So now I know. I'll check it up. I'll check it out. Yeah, okay, what does this mean for neural fields? It basically means there's nothing fancy going on. Okay, but it also gives you another angle, which basically tells you now you can actually go and you can actually study what this kernel might look like, and you can design that kernel, right? That was the flip side of it. So we understood that this is true. Now we can design neural networks that have particular kernels that are particularly good for certain signals. And this is actually what this paper did. Fourier features that networks learn high-frequency functions in low-dimensional domains. Actually great. So these guys actually went all the way. I didn't understand this back then. They figured this part out about the relationship to neural tangent kernels. So this is in fact the neural tangent kernel for a 4-layer value MLP with one scalar input. So you have one input, which is an x, like x on one axis, or x1, right? So like imagine should always label your axis. But imagine there would be x1 here, and then on the other axis there would be x2. And this is exactly the neural tangent kernel between x1 and x2. This is actually what this kernel looks like. So this basically tells you what is this kernel function of the neural network look. And now just for the record, this kernel, imagine that every value would just be close to like a nice property to have would be if this thing looked like this. Wait, sorry, I actually forgot about the slide. So now I have to go back and think about it again. Right. So I can explain it in a hand-wavy way, but I must admit that actually I have forgotten the exact details of it. But basically, in a hand-wavy way, what this tells you is basically that if the x-coordinate at test time is close to the x-coordinate at training time, and those, like, if they are close and you expect them to get a high value, then you should see a diagonal here. So basically, this diagonal means that the kernel function will be large if the input coordinates are close at training and test time. That's basically what the diagonal means. And as you can see, this is not what the thing of a value neural network looks like. This is what it looks like of a value neural network, which basically means that if the two values are only if the two values are literally now I remember it. Only if the two values are literally identical. So if both of them are 0.5 or if both of them are minus 0.5, then the neural tangent kernel of the value neural network was large. So these are similar. But the moment one of these two coordinates went went off, like the neural tangent kernel drops off dramatically. So basically, it's a kernel that is local only if the two things are similar. Is that right? Okay. Okay, take that with a grain of salt. But basically, what this paper did back then is basically they said, okay, let's take a ReLU neural network, but let's, instead of changing all of the weights of the neural network, let's instead take the input and just apply a mapping to the input, which we call a feature embedding. So like you might see many neural field papers or many papers that use NeRF and stuff like that, and they talk about feature embeddings for the first layer of your neural network. And what that means is you take the input coordinate x, and you just apply some function to x, and you do that many times. So like, let's imagine this function, for instance, could be a sine. So you might apply a sine to the x, like this. So this is then a sinusoidal embedding. This was actually proposed first by someone who's going to give a guest lecture in our class, Ellen Zhong. She used this for cryo-EM 3D protein reconstruction with distance with occupancy functions. And then in NeRF, this was basically what was used. This is what they used. So basically, you take your input coordinate and you compute the sine of the input coordinate, and then you compute the cosine of the input coordinate, and then you concatenate them. So you do like sine, cosine, then you increase the frequency of the sine and the cosine. So you increase the 2 to the I. The I gets increased by 1. You compute the sine, cosine again. You increase the I by 1, compute the sine, cosine again, and you just concatenate it to one big vector. And then that's what you feed to your ReLU neural network. So you don't feed the coordinate directly, you feed in this like sine cosine embedded thing. Other people have proposed other things. So you, for instance, can say, oh, I'm going to use a Gaussian embedding. So I pick like some 2D point in my input space, and then I compute the distance of my coordinate to that 2D point, and stick it into a Gaussian. So I place a Gaussian in my input space. And then I have lots of these, and each of these Gaussians gives you one of these embeddings. And then that's what you give to your neural network. Does that intuitively make sense? Good. And so it turns out that what this is actually doing is it turns out this is designing the kernel function of this function end to end. So like now, after training your neural network will still make predictions according to this kernel function, but you have now changed to the kernel function. And it turns out that these different kind of embeddings are very interpretable. And we're not going to derive it, but actually, if you want to come to my office hour, I'll derive it for you. It's a very fun thing. For the sinusoidal embeddings, you can show that the kernel function it induces is exactly a Gaussian. What that means is that your neural network will make similar predictions if the coordinates are close in 2D space, like literally close in a Euclidean sense. And so that, for instance, seems like it's a very useful kernel function to have for your neural network, right? Whatever. And this is now what we can also understand sine with, which I didn't understand when I wrote this paper, but basically what the sine cosine functions do, what the sine cosine activations do is they just induce a different kernel, and this kernel allowed you to basically quote unquote overfit on the training set and made this kernel really peaky, and that's why we were able to like fit this high frequency detail in this room much better than without it. Yes, Caro.
Is it that in like these type of networks because making your kernel more peaky, you need more data?
Yes, that's exactly what's happening. And that is literally, so the question was, do you need more data to fit the thing better? And the answer is exactly yes. You previously circumscribed it as like just being overfitting, and this is exactly what's happening. The neural network basically has more degrees of freedom. And so if you want the same kind of, if you want it to still be accurate everywhere, you need to sample much more densely at training time. Yeah. Yes?
Would it make sense to have those embeddings and the sinusoidal activation functions like together, or would that be like?
Yeah, it could make sense. It could not make sense. I think the answer that kind of everyone converged on in the end is you now can just design this kernel function for your specific application, and like different activations induce different kernel functions, and for your activation, it might make sense to do that. But generally, so the thing is, there's like really no true answer. Like, yeah, and they also showed they also showed like results on like different kinds of signals. So like here's an MRI image, or here's an image, or here's a sine distance function. Okay, and since then there's actually been a few other papers that do similar things, like dictionary like a dictionary embedding for each 3D coordinate, or Gaussian. This uses Gaussian activation functions. And this is actually kind of close to another paper that it's not close, but maybe if you guys heard about 3D Gaussian splatting, if you're on Twitter, you might have by now seen it. Who has heard about 3D Gaussian splatting? Okay, a few people. It's very cool. I'm going to get to it. But that is kind of reminiscent of that, I guess. Okay. Yeah, another cool thing, which we're not going to talk about, but I just want to call out. And there is actually, so now that we already know that neural networks kind of aren't magical in any given way, in this context at least, right? In this context, they don't do anything special. They're just like better souped up interpolation kernels. Some people asked, okay, so do we actually even need a neural network? Or are there certain properties we would like to have that we can design functions for that maybe are better? So let me give you one example for this. There is actually neural fields that have analytical Fourier transformations. So if I give you a neural network that is defined on, like, imagine I give you a neural network that I fit to this cute little 2D function there. And now I ask you, please give me the Fourier transform of this neural network. So just for the record, right, Fourier transform is like a transform that takes a function as input and outputs another function, which is the Fourier transform of that function. How would you do that with your neural network? Has anyone ever tried? Who has ever thought about doing a Fourier transform of a neural network? No one. Okay, so a neural network is a function, so apparently you should be able to do a Fourier transform of a neural network, right? And theoretically, the answer is yes, but if you still remember from learning about Fourier, who has learned about Fourier transform? Who knows what a Fourier transform is? Like everyone, okay. So if you remember how Fourier transforms work, it's this integral transform. Like you do this integral, then you have the function, and then you da-da. And then in high school, in college, you had to like derive a bunch of Fourier transforms of a bunch of functions, right? I'm sure you've never done that again. If you tried doing that with a neural network, good luck. It's going to be like value of this thing, of value of this thing. Like it's a bunch of like composed values with like affine transforms in between. There's in fact no way you can analytically derive the Fourier transform of any neural network. But if you used your neural network to parameterize a signal, wouldn't it be grand if you would have access to the Fourier transform of the function? So let me give you an example why you might care about that. Let's say you knew that the signal you were interested in was had a particular structure in the Fourier domain. For instance, it didn't have any high frequency detail. Then what you really would like to do is you would like to fit your neural network to that signal, and then you would want to regularize it to not have any high frequency detail. And that would be very easy if you could analytically derive the Fourier transform of your neural network, because then you could just say, okay, make sure that these parameters that like make it high frequency aren't, okay. But unfortunately, that's really hard because neural networks don't have analytical Fourier transforms. So there have been a few papers in the last few years. Some of Bacon is a kind of a funny paper title. This is David Lindell. He was my old lab mate, and he also wrote Siren with me. David is now faculty in Toronto. He wrote this cool paper where they basically showed that you can basically build a multiplicative network where basically you always have like sine of ax plus b times sine of ax plus b times like something like that. So it's multiplicative as opposed to being composed, right? If you had a neural network, it would be sine of ax plus, get the idea? So it's not composed, it's just like a series of multiplications, and it turns out that that does have a analytical Fourier spectrum, and they showed a bunch of cool applications for that. So I'm sure there's more to come along those lines. Actually, one of the first projects that David thought about when he joined our lab was related to this kind of line of work. Okay, and if you're interested in this like neural field stuff, we wrote like a whole report about it, and we like every conference, CVPR, NeurIPS, SIGGRAPH, we always go around and we give a tutorial on these neural fields. So if you're at one of these conferences, you can come to one of our tutorials. The CVPR one was really big. It's really fun. Okay, so neural fields, however, long story short, are just another way of parameterizing the signal. Nothing special, nothing to see here. Neural fields have a few cool properties and a few not so cool properties. One, the storage does not immediately grow with the spatial resolution that you want to encode, or the number of spatial dimensions. So for instance, if you have a function that is defined on 10-dimensional input space, right? You can't store it as a voxel grid. There's no way you can store it as a voxel grid. It's not happening. It's way too big. But you could store it as a neural network because the neural network doesn't care. It just takes a 10-dimensional coordinate as input, gives you some output, you train it, done. Great. So that's a cool property. And the memory you require also doesn't scale with the resolution, not immediately at least. It kind of scales with the smoothness of your function. If your function is like very non-smooth, then you probably need more parameters to like parameterize the decision boundary that gives you that function. But if your function is really smooth, you probably don't need as many parameters. And now comes the biggest downside of these neural fields, which is kind of why people aren't, well, this is one of the key reasons why people might not consider using them. Sampling them is ultra expensive. If you have a voxel grid and I give you a 3D coordinate, sampling is immediate. It's a lookup in an array. For a neural network, for a neural field, I give you a 3D coordinate. You have to do a forward pass through a neural network. And forward passes through neural networks are really expensive. And now imagine you want to sample a sign distance function on a regular grid, for instance. You want to get the sign distance function of this room. Well, you have to sample your neural network as many times as however densely you want to sample the function, which gets really expensive. Similarly, training your neural network to fit functions is also really expensive. If you want to, I don't know, if you want to like write something into a voxel grid, you just copy it into the voxel grid. If you want to write something into a neural network, you have to do gradient descent until your neural network says the correct thing, which is much less exciting. Another problem with these neural fields, which actually by now there is some papers that try to fix this, is that they don't expose localities. So like if you have an image, you can do a convolution on an image. Right? If I give you an image as a grid, you can stick it into a convolutional neural network, and your convolutional neural network will filter the image. If I give you a neural field and I ask you to compute the convolution of this neural field with some other kernel, that is really, really hard. And you can it's kind of the same, is as hard as doing the Fourier transform of a neural network. So convolving a signal that is parameterized as a neural field with something is really hard. And the reason why people are still excited about them sometimes is because they actually have this property of over training. They basically automatically assign parameters to the areas with high frequency detail. And that is something we don't perfectly understand yet, but basically they can still encode very, very complicated functions with very few parameters. And this is something that people are still excited about. Okay, so this actually concludes our discussion of neural fields. Does anyone have questions? Yes?
It seems like, I think you mentioned, I missed it, but like training something like an occupancy field, like neural field from mesh representation, seems like to get the actual training data for it, couple points, and then do like computation you talked about that's heavily expensive, about like what the labels are.
Yeah.
Things. Is that the case, or is there some other?
There are, excuse me. And yes, there are. So the question is like, to fit a neural network, like to find the occupancy function for a thing, is there any other way than literally supervising the occupancy function of your neural? And the answer is kind of usually not. There are some exceptions. So it turns out for sign distance functions, for instance, there is a way of actually not having access to the ground truth sign distance function, but instead maybe only having access to the point cloud of your 3D shape, but then still being able to train a neural network to parameterize the sign distance function. But I wasn't intending to talk about that. It basically relates to, like on a high level, you can say that some functions are the solution of a boundary value problem, so of a differential equation, right? So sign distance function turns out are the solution to a differential equation, and you actually know what that differential equation is intuitively. The differential equation is it's 0 on the surface, so that's the boundary. So it's 0 on the surface. The sign distance function is 0 on the surface, and then the norm of the gradient has to be 1 everywhere. And you know that that must be true because the sign distance function tells you the distance to the closest scene surface, which means that as you go away, the distance increases linearly. So like the norm of the gradient has to be 1 everywhere. So it turns out that just with these two constraints, you can actually, that fully defines the sign distance function. And it turns out you can train your neural network like that. You can sample points on the surface. And for those, you say the neural network output should be 0. And then you sample a point off the surface and you say, well, I don't know the value of the neural network, but I know that the gradient should be 1, like the norm of the gradient. And at these points, you just supervise the norm of the gradient. And actually, that's how the sign distance function was fit for the room scale theme there. But we're not going to discuss that in too much detail. Good question, though. Yes?
So for something like an occupancy grid, I imagine it as something that is like almost binary, so inside 0, outside 1, or the other way around.
Yeah.
And so if it's like a binary field is like not differentiable, right? So how can you train something on something that's not differentiable?
Actually, I mean, you train neural networks on things like when you say a binary field is not differentiable. You mean it's not continuous because it like switch. Okay, and that's totally true. So what you do in practice is you get like a continuous version of it, which basically it's the same as saying that like a classification network isn't, like classification is also not continuous, right? And you can still fit a neural network to do classification. It's the same thing. Yeah, you basically get, yeah.
But then how do you make the decision after, like where exactly to draw your boundary?
Usually what people do is you say, well, usually the way you do it is you say like the 0.5 level set, for instance, for occupancy is my surface. And then all the points outside you supervise with 0, all the points inside you supervise with 1. And then you actually might sample points on the surface because you know what these points are usually. And for those points you just say the output should be 0.5. And then you have a sigmoid on the output and then you kind of get the right thing. Good question. Any other questions? Yes?
Sorry, this kind of relates to the earlier stuff, but like how do you get from like the side distance?
Um,
Isn't there like
sorry, when you say, the question is how do you get from the sine distance function to a 2D representation? To like an image, you mean?
yeah, like because like previously in those slides I saw like
We're going to talk about that in 2 lectures from now. But so the question that you're asking is actually one of rendering. You're asking like, look, I have a 3D function, and now I want to render an image of the 2D function. And specifically, I want to render the image as if I shot a ray, it stopped on the surface, which we know is the 0 level set. And that's exactly what we're going to talk about in 2 lectures from now. Is that okay?
Yeah.
Cool. But yeah, good question. So, and then the other way you actually know already, or like the other way is I give you the 3D sine distance function and then you do marching cubes. Like you sample it on a grid, and then there's this marching cubes algorithm which basically tells you, like, do you remember that from last lecture? Like, let's just briefly recall that. Like, you basically have your 3D function and you sample it on a grid, and now for each voxel you basically ask, does the sine distance function change the sign between any 2 corners of the voxel? And if it changes the signs, then it tells you there has to be a surface there. And then you can actually like reconstruct the surface that is encoded in your sine distance function. And then you have a mesh, and then you can render the mesh. Yes?
Do these like neural fields take like images directly?
You can fit a neural field to any signal that you have access to, yes. So, but we call the neural field, like, this lecture is kind of a little bit strange because like the way to think about it is I gave a whole lecture on a topic where I basically tell you this thing is like a voxel grid. Like a neural field is like a souped up voxel grid. It's like a thing. It's like a grid of pixels, except that with like asterisk. But basically, it's just like a voxel grid. So you can fit. In fact, this used to be part of the homework. I had a homework. Did you kick that out? That part where people just fit a neural field to an image. Great. So in homework number 2. You're actually going to convince yourself of this fact because I'm going to ask you, here's an image, fit a neural network to it. And then you end up with the weights of the neural network, but it's just a neural network. And then I can similarly ask you, I can give you a grid of pixels and I can ask you fit this grid of pixels to the image, which seems like a stupid thing to do because you're like, I already have a grid of pixels. So like, why don't I just copy them over? But it's actually exactly the same thing. You can define a loss on your grid of pixels. You have 2 grids of pixels. One is randomly initialized and one is an image. You can define a per pixel loss that says, oh, what's the distance between these 2 pixels? And then you can optimize the values of one of the grids with gradient descent. And that's actually what you're doing when you're fitting a neural field. Just that it's like, that's a good way of thinking about it. There's like nothing else happening. Does that make sense?
But why would you ever want to do that besides like compression?
Ha, great question. Well, no, I actually just told you a few reasons. Like, they're actually here right here on the slides. Like, one reason is because, like, compression is actually one that is fair, but actually compression is not the critical one. It is actually, it's kind of the flip side of compression. What does compression mean? Compression means you need less memory to store more detail. And now imagine you want to store this room photorealistically. I want that every hair on your head is represented perfectly. Okay, so now imagine what the resolution of the voxel grid would be that can manage that. It's going to be a billion voxels wide on the side length of the room. So that's not happening. That's not happening in 5 years. So what are we going to do? Well, one way is you can fit a neural field, and it turns out the neural field might not, okay, it might not manage that, but it'll get a whole lot closer than the voxel grid that you can have, basically. So, and this is actually the reason, until very recent, like, there just like 2 months ago, a paper came out on like that many people still use these neural fields for exactly that reason. Like it turns out that if you just grind it out and you are willing to take the computational expense and like wait how long it takes to fit the neural network, they still give you super high detail as a function of the memory that you need to store them. And like when I say memory, like it sounds like that's like negotiable, but it's not negotiable. If like the memory that you would require to store a scene is a terabyte, it's not happening. So like the neural field basically allows you to kind of get around that. Does that make sense? But good question. But other than that, honestly, the answer is there might not be another reason. So it might be that this kind of there are other certain things with like solving differential equations for which these might maybe be useful. There's like a whole thing in physics called physics-inspired neural networks, which are basically neural fields. But other than that, in graphics, it's not clear if they will have many other use cases. Which is by itself useful, because if you go to CVPR this year, I promise there'll be 100 papers on neural fields. So it would be useful to know that maybe this is useful context for putting these papers into a framework. Actually, it's going to be 1,000. I think how many papers are there at CVPR? There's 10,000 papers? No. 6,000. How many papers are there at CVPR? Who knows? I think it's like 6,000, right? 6,000 papers. So I think last year there were like 600 papers on neural Rayleigh fields or something like that, which are like that, right? Okay, good. So now neural fields. Actually, this we're going to get through, I promise. So this is a cool topic. So this is something that still remains very relevant today. And now we're getting into generalization territory. We're going to talk about something that's actually useful to machine learning. Crazy. So hybrid parameterization. So it turns out there's something in between a discrete parameterization and a neural field. And these are called hybrid parameterizations. And what's the idea of a hybrid parameterization? The basic idea is you take a voxel grid, and the voxel grid is kind of low resolution. And the voxel grid stores a feature at every, stores features. And now if you want to query a value, you go into the voxel grid, maybe you do interpolation. You interpolate the features that are stored in the voxel grid at that coordinate, and then you stick it into a neural field, like into a neural network, and the neural network gives you the final value. Let me repeat that. Imagine you wanted to parameterize the occupancy field of a 3D, you wanted to parameterize a 3D occupancy function. You're going to have a low resolution voxel grid. The voxel grid is going to store features like 16-dimensional vectors at each of the corners in each voxel. And now if you want to get the occupancy of a particular point, you go into the voxel grid, you do trilinear interpolation, you get the value, and you give that to a neural network. And now the neural network decodes it into the final occupancy value. Okay, so does that make sense? Okay, good. Actually, here's a fun fact. Like, you don't have to use a voxel grid. You can use any kind of discrete data structure. Here's another example for a perfectly valid parameterization. You can say, well, I know that the most variance of my scene is explained on the XZ plane. Like, my scene mostly varies on the XZ plane. It doesn't vary as much on the other planes. So what I'm actually going to do is I'm going to have like a ground plane. So it's kind of like a grid that is lying in the 2D space, right? And now when you want to decode a 3D coordinate, what you do is you orthographically project it onto the ground. You drop it onto the ground. You interpolate the grid at that value, get a 2D coordinate out. Sorry, you get a feature, right? You do bilinear interpolation in this case. You take the point, drop it onto the ground, bilinear interpolation gives you a feature. And now you take the feature and now you have to give it this distance as well, or you just give it the whole 3D coordinate p, doesn't matter. And now you give that to your neural network, right? And what I want you to think about is like there's basically like this is kind of a way of interpolating between parameterizing everything as a neural network or parameterizing everything as a grid. You can basically, on one end of the spectrum, parameterize everything as a grid, or you can basically say, I'm going to discretize some of my dimensions, like the ground plane, and I'm going to store discrete values in the ground plane, and then I'm going to decode the rest via a neural network. And intuitively, what you can imagine is that this neural network now has to do much less heavy lifting. The neural network now has to only basically imagine, like, this is not actually what's happening, but it's kind of like the neural network only has to like parameterize like the variance of like each little cube. So it only has to store a relatively small set of small functions that explain the variance over every cube. Does this kind of make sense? Yeah, great. And it's worth pointing out that this doesn't make any assumptions on the function that you're storing. This is just as general as like parameterizing the whole scene in your neural network or parameterizing the whole scene as a voxel grid or something. The only trade-off you're making really is like how long does it take to query my function and like how long does it take to fit this thing. Like just to be clear, if you were to fit this, what you would still do is you would now make this grid learnable parameters. So each of these features is learned and optimized via gradient descent, and you would do exactly the same thing. You take a coordinate, you do interpolation of your grid, you get the feature, you stick it into a neural network, you get an output, and you do gradient descent. Or like in this example here, right, just to be clear, you could say, oh, I'm feeling like I'm going to discretize this axis, and I'm going to make this an array, and in each of these bins, I'm going to store a feature. And if I want to get the value of this coordinate, I'm going to drop it onto my bin. I'm going to interpolate the feature, like F1 and F2. I'm going to interpolate these two. I'm going to give this to my neural network, and that's going to give me the occupancy value. So, and that's what you can do. Okay, so, and then you can go crazy. You can say, oh, I'm going to not have one plane. I'm going to have 3 planes. I'm going to store 3 planes in space, and I'm going to do this. And okay, I'm just going to show you the application of this, what that actually, do I have an, oh no, the most important paper I'm missing, that's name. Okay, okay, so that's, so you can pick like 3 planes, so 1 ground plane, and then 1 plane for this axis, and 1 plane for this axis. And then you just concatenate these 3 features, right? In this case, you get 1 feature from the ground plane, you get 1 feature from this, you get 1 feature from this. And then you decode it. Or, and now this is starting to be interesting, let's say you have an image. I take a picture of the scene, right? And now here's something that you already know, and we're going to talk about this more later. You know for a fact that when I take this image, every pixel tells you something about the information that lies along that ray, right? Like if I take this image, you know there is basically one way of to think about it is to shoot an array from the camera, and whatever the color is of the point that you're hitting, that's the color of the pixel, right? So wouldn't it make sense to say, oh, if I have a 3D coordinate and I have an image of the scene, to basically take the 3D coordinate, project it onto the image, and maybe I'll get some information from the pixel at that coordinate, and I'm going to use that information to predict what the value of that function should be. So like you can imagine this is kind of connecting a 3D function that is defined in 3D to an image that you have captured of that 3D function, right? You can you can say I'm going to store information about my 3D scene in an image that I capture from the 3D scene, and I'm going to extract that information by taking a 3D coordinate, projecting it onto the image, and getting the information in the image. We're going to talk about more why that would make sense, and this is just like as a high-level idea. Here's another thing that people can do. We already talked about multi-scale voxel grids, right? So you can do the same with a multi-scale voxel grid. So you have like, I don't know, you have like an octree, and then you're going to get like store features in your octree. You can do that. And people have used this as recently as 2021 to store really high-quality 3D geometries like this sign distance function. And here, basically, it shows you why people were interested in this. It's kind of a trade-off, right? On the top left, you have a really low-resolution voxel grid. So the neural network has to do most of the heavy lifting. It's kind of like just having a neural field that encodes the whole shape, right? A neural field is a special case where you just have 1 voxel, and then you encode everything with the neural network. And then as you increase the resolution of the voxel grid, basically, it gets easier and easier to store the model. But of course, it gets more and more expensive to store the voxel grid because you have to store. But it's a neat way of trading off. So this is multi-scale voxel grids, neural geometric level of detail. This was an NVIDIA paper from 2021. So here they actually compared Siren. So now you know what each of these are. DeepSDF was just a ReLU neural network. Then Fourier feature neural networks, that's one of the papers that we talked about with the sine cosine embeddings. Siren, that was my paper. I actually think it doesn't look like that bad. I think I could do a better job, but still the point stands. Like this is this thing. Like it is definitely true that the only thing that actually worked was like this voxel grid. So if you try to fit your neural network to this very complex 3D fractal, it didn't work very well. Okay, and now here's a funny one. You can have a multi-resolution voxel grid. So if this sounds like a lot, it's just because we don't want to spend too much time on it because there's like not that much interesting stuff going on here, but you still should hear about it. So I'm not saying that these papers aren't interesting. They're very good papers, but like this particular aspect of them isn't that interesting. So one thing you could do is you could say, oh, I have one low-resolution voxel grid, and then when I want to query a 3D coordinate, I take my 3D coordinate, I query the voxel grid, I get my interpolated feature at that low resolution. Then maybe I have one higher resolution, slightly higher resolution voxel grid, and I'm going to query that one as well, and then I get another feature. And you might want to do that on and on and on, but of course at some point, as we discussed, it gets too expensive because the voxel grids get too big. Well, what could you do? You could use a 3D hash function. So you could do a thing where you would take a 3D coordinate, you hash it like a classical hash map thing, and then your hash map will just store lots of feature vectors. You take a 3D coordinate, you hash it, you get a feature vector, and that's also one of the inputs that you throw to your neural network. So you basically have your voxel grid, you sample your multiple resolutions of voxel grid, and then you also sample your hash function and you concatenate that and throw it into the neural network for good measure. And that's what this paper here did. This was the SIGGRAPH Best Paper 2022, Instant Dual Graphics Primitives via Multi-Resolution Hash Encoding. Kind of tells you what they did. And we didn't talk about differentiable rendering yet, but actually this is not differentiable rendering. This is here, they just fit exactly like you asked earlier, like why would you want to store an image? Why ever would you want to store an image? This is a gigapixel image. So this image has like, I don't know, 1 trillion pixels. Okay, gigapixel, I guess it has 1 billion pixels. But like, so this is a really big image. So if you stored this in a grid, it would be really expensive. But you can store it in this multi-resolution hash encoding, where the neural network is basically doing a little bit of interpolation, and it turns out you can store the super high-quality image in like relatively few parameters. Or here, this is an occupancy function or a sign distance function. Similar, super high level of detail. This, by the way, was the gradient descent that you're seeing here. So this is gradient descent from random initialization to fitted occupancy function. I think this is real time. It's really fast. This is a neural radiance field. So this is with the differentiable renderer. Again, like this is the optimization process. It's relatively fast. And then I guess they also fit a cloud, because why not? Okay, so this was 2022, but now you understand on high level how this works. There's like lots of, obviously, details that you skipped, but on a high level, this is how this works. Any questions to that? Here's another thing you can do. You can, instead of having a voxel grid, like you can mix and match, right? Or you can say, oh, I'm going to store features that I attach to points in a point cloud. And now what I'm going to do is if I want to get the value of my occupancy function at this coordinate, I'm going to find the n nearest neighbors. I'm going to get their feature vectors. I'm going to get the feature vectors, concatenate them, and now I'm going to concatenate like the distance to each of the 3 points as input as well, and then I'm going to fit it to my occupancy function. Might be another thing you could do, and you can do that. This paper is called value fields. This is also an interesting thing. You recall bilinear interpolation. So one thing that this paper here did is it basically said, maybe you don't need the neural network at all. What does it get you? Like, okay, so this is this hybrid neural field representation. You have your voxel grid, you query the coordinate, interpolate the features at the 4 corners, and give that to a neural network. Or alternatively, maybe we don't need the neural network. We just give it directly to a value. What does it buy you anything? Turns out that buys you a lot, because instead of just linear interpolation, which can't have discontinuities, this already buys you that you can have discontinuities, and you can actually fit it via gradient descent. And they showed that, and it stays super fast, right? It still is super fast. It's basically as fast as querying your voxel grid, because you just have to put it through one value, which is like very cheap. So they showed that like, as opposed to like just linear interpolation, which is the yellow line, you can get like a much better approximation of discontinuities, so that's really cool. And then they showed that like you can still fit it really fast. So this is the fitting time. So this is better than a voxel grid, but not as expensive as a neural field. And now this is the conclusion of hybrid representation. So basically, this is just a way of trading off the memory with the memory that your representation requires with the compute that it takes to sample and to fit. Right, with like a voxel grid, you can query it really fast, but it takes a lot of memory. With a neural field, querying is super slow and expensive, but it doesn't take a lot of memory to store. And this is kind of just a way of trading off. This is something that is still being used today in lots of applications. The neural network is kind of just doing a little bit of interpolation, you can imagine, between the feature, like information is stored in the grid, and the neural network is kind of doing a little bit of interpolation. And this has applications in generalization, which we'll get to later. And now, I think we're going to talk about this next time, but this is actually basically the end. And the next lecture will be about about rendering. So it's going to be about light transport and rendering. And then we're going to finally talk about differential rendering, and then we end game. Then we can just, from there on, talk about just neural networks and reconstructing the 3D world, and how can we train neural networks to reconstruct the 3D world from few observations and all of that funny stuff. Thank you. Hi. Yeah, you can.
Okay, yeah.
Thank you.
Of course, thank you.
Thank you.
Yeah, did you submit?